So, hello everyone, welcome to the week 4 of the problem solving session for the design and analysis of, data structure and algorithm design course. So, the topics for this week were a brief introduction to linked lists, and there was one problem that was discussed, which is called RMQ, or range minimum query. Okay, so so just to recall, sorry. Okay, so just to recall, what is the problem? The input to you is an array A of length n, and you are given two indices I and j. So let's say I and j, let me just call it L comma R, and these are two indices, okay, from 0 to n minus 1, and what you want to output is the minimum value among a l plus 1 all the way up to ar. Okay, so that is the problem that we studied. So for example, if your array is if the input array that is given to you is let's say 7, 29, okay, so let me number these as well: 1, 2, 3, 4, 5, 6, 7. Okay, so the overall minimum element in this entire array is this, but the input consists uh, two positions, L comma R. So let us say um, L is 3 and R is 6. Then what should be the output? You are essentially looking at this part of the array, right? Only this part, and forget about the rest of the array. Look at the minimum within this array, and that happens to be 4. So you'll output 4. Or one modification that you can think of is, don't just output a minimum element, output the index as well. So in that case, you will output that the minimum in A, L to R is at index 6. So that is one modification you can think of. But if you can solve this, if you can solve the value, then you can also find the index. That's not a big deal. So for the sake of discussions, I will probably not even talk about this. But if you know a way of finding the minimum, then you can as well store the indices. That's just some extra memory that you are keeping track of. So you will also be able to extrapolate this. Okay, so so what is the trivial algorithm for solving this problem? Like, what is something you can think of? Okay, linear search. So okay, so linear search would mean that you're spending order and time. So if you do a linear search, then you are spending order and time, and there is no extra space. So auxiliary space is nothing. You're not really storing anything. I'll just say it's order 1 or something, because you may want to store some comparisons. You want to maintain a minimum so far. Okay, but okay, but so this is a linear time algorithm. It tells me minimum in the given subarray in order and time, and it doesn't even take any space. But I'm not happy with it because um, what if I need, let's say I don't have one query, I have thousands of queries, they keep on coming one after the other. Okay, so um, for like, let's imagine that this is a huge array. It's of like very very large size, and um, these queries are very frequent. Okay, so suppose the array size is very large. Okay, that means, let's say, um, okay, let me just say it's um, 10 to the 5 or something. Okay, it's just a random number. Okay, and let's say I am not just making one queries, I'm making many queries. Large number of queries. Okay, so how so let's say I'm making 10 cube number of queries, and so what is the running time for the entire algorithm across all queries? If I were to run this algorithm. mm, okay, so each query takes um, some c times 10 to the 5 amount of time, and there are 10 cube many such queries, so total time would be c times 10 to the 5 times 10 to the 3, which is c times 10 to the 8. So that is a large amount of time, right? So if this increases, then the number of queries increases, then your time is exponentially increasing. So even though you are doing linear search time, which sounds like it's very fast, because for most problems we don't even know how to do linear, but the issue is that if I am making too many queries, or if my array is large, then I'm actually spending a lot of time. So um, so what if I could use some extra space? I'll use some extra space and make sure that each query time is reduced. Okay, so the array size being large, we cannot do anything about it as such, because that's the input that's given to us, right? So this is something we are not even going to touch. So can we make some improvement on the second issue? That's the question. So if I could somehow bring this 10 cube down to um, order 3, okay, which is an exponential improvement in terms of time. So if I could do that, then the total amount of time that I would end up spending across all queries is just order 10, like it's just 3 times 10 to the 5 or something, right? So that's the motivation for improving this down to, we want to make this sublinear. So by that we mean we want little of n time, something that is asymptotically smaller than n. So this could be log n, this could be square root n, or n log, or something like that. Okay, at the cost of saving time, we would end up spending, like we would end up using some extra space. So that's the idea. So there's always this space time trade off. If you want to save on time, you would end up using more space, and uh, if you want to reduce space, if that's the resource you care about, then you would end up uh, spending more time. So that's the, yeah, there's a general trade off that's central to these problems. So that's the idea. Okay, so even though it was a linear time algorithm, we are not happy with it. So can we save time at the cost of uh, extra space. So that is the question. So can you think of something better? Can you get this time down? um, I hope this point is clear. Yeah. Merge sort and binary search. So what do you mean by merge sort? Because if you use a sorting algorithm, notice that, okay, like if I do a sorting here, then what would happen is you get minus 2, 2, 4, 9, sorry, 7, 9, 11, 13, and 29. I hope I'm not missing anything. But now if you apply the range minimum thing here, okay, like, so this is 0, 1, 2, 3, 4, 5, 6, 7, and your indices were 3 to 6, right? So now if you apply a range minimum query here, your algorithm here, the output would be 7. But that's not correct, because in the process of sorting you have changed the order of all the elements. So if you so all these indices are now like they have the order is completely disturbed. So on this sorted array you cannot run a range minimum query. So okay, so you don't want to apply it on this part, but if you do, um, if you're doing a sorting algorithm, okay, let's say the size of your let's say the size of this um, subarray is 4, which is, let's say, n by 2 for us currently, right? It's half um, the original size. Okay, so now you, if you apply your sorting algorithm here, you would be spending at least n by 2 times log n by 2 time, which is worse, right? Because your sorting algorithm requires order um, n log n time.
Can you repeat the problem formulation once? Can you repeat the problem
Sure,
formulation
sure.
again?
Yeah, this is the range minimum problem, range minimum query problem. The input to you is an array A with n elements, and then you're given two indexes L and R. The question is, given this L and R, look at that subarray and find the minimum within that subarray.
Okay, thanks.
Okay. So, so what do you mean by binary search? Can you explain the algorithm, um, Asma? Okay, so I hope the point is, I mean, I hope I could convey that sorting is not a good idea here, but if you have any questions, feel free to ask. Okay. um yeah, so how, so any more ideas on how we could save on time? I don't want to do it in order and time.
So, but then what is preventing us from using sorting here? Say, if L and R indices are given to
Hmm,
us,
hmm.
then why don't we pick that much portion of the, I mean those elements from this list, and then do the sorting and apply binary search? I mean, not the binary search. Since we are looking for the minimum element, so we can perform a good sorting here,
Hmm.
and we can find the minimum element, say in an effort of the order of n log n kind or
Hmm.
something.
But
So
that,
why sorting is the bad idea?
because your linear search is doing a better job, no? You just go through that sub array and keep a track of which is the minimum element you have seen so far. That will only take you order and time.
Okay, but do we know this minimum element in advance to perform the linear search? We know this minimum element in advance. No, we do not.
You know the minimum element in advance. No, no, no.
In order to apply the linear
Huh,
search
huh,
within this range,
huh.
right? So to apply the linear search, we would be looking for the occurrence of some element within this range. So what that element is, I mean, how are we using the linear search to get the minimum element?
Okay, so you start at 3 because the L that's given to you is 3. So this is L and this is R, and the current minimum so far is 9. So minimum currently that you've seen is 9. Then you look at the next element and look at the next element and see whether the current minimum is smaller than this element you've seen. So between 9 and 11, 9 is still smaller, so you retain this. Then you look at the next element, compare this with 9, again it doesn't change, and then you go to the next element, compare 9 with 4, and now you have an updated minimum. So I mean, this is the trivial way of doing it, right? So just scan for the minimum.
Well, in that sense, I mean, some sort of bubble sort kind of look in one go, one iteration of the bubble sort.
Yeah, and you are not changing the values as well. Like they are, it's an in place thing, right? You don't, don't alter the array. But we did not use any space as such. The only space we needed was to store this minimum so far. That's all. But yeah, if you are okay with giving more space in the hope of saving time, then what would you do? Okay, there's one answer in the chat. It is okay. This n by 2 log 2 um, is because if you use any sorting algorithm, then if you apply it on an array of size n, then the time that you will need is n log n. Okay, and here in this example, the size of the array was half of the original size, which was n by 2. So therefore your array size is now n by 2. So we are just replacing n with n by 2, that's it. So this becomes n by 2 times log n by 2. Is that clear?
So how can we do better than linear one? Because I'll have to traverse that subarray at least once to find the minimum element.
So what if you could store something, right? So you have space to store, right? So what you would do is, let's say I'll keep a table. Okay, in my table the values of L, potential values of L, are anything from 0 to n minus 1, and the potential values of R are anything from 0 to n minus 1. So what I'll do is, okay, what does it mean to I and j? So when I look at this table, let's say I look at the ith row and the jth column, what this means is this stores the minimum value from in the subarray I to j. Okay, so from that, within that entire array, you're only looking at this part, discard everything and find a minimum here. Okay, so if I had some way, if I had this thing, okay, like I have a table where all the values are stored, so what would you do? How much time would it take now? You just
Yeah, so because since you have constructed this table, so this reminds me of using some dynamic programming kind of the thing. I look for up, left, right, up, and then we can somehow reuse the values and then really do
So,
things.
so let us assume for now that you have the table that's given to you. So we are not talking about time required to create this table. Let's say you have this table, and now a query comes. So query is I comma j, let's l comma r. Then how would you output now? You want to tell the minimum between these two values.
Oh, so I will refer to this table and then come to that point, and this will give me the minimum number of the
Exactly.
comparisons.
So what you would do is just look at the table. So let me call this lookup table. So we refer to the lookup table and look at this value. Let me call this matrix M. Look at L comma R value in this matrix and output that. Okay, so this is just order one time um algorithm. What it does is given I comma given L comma R, it will just look at that entry, look at the value and output that. That's all. So from order n time, okay, you have reduced it all the way down to order 1, but at the cost of space. So how much space are we using for this? How much auxiliary space did we use?
Of the order of n square.
Correct. So you're doing order n square space. Now the question comes, how do you construct this table and how much time does it take for constructing, which is what you were referring to, I think. So what is the time required to construct this table?
So what about the values in the first row and the first column? What would that mean? So 0, if we start from 0, so the values in the first row would be all zeros, isn't it?
No, no, no.
Because this,
Huh.
Time,
So
time.
sorry. Okay, so if you look at 0 comma 0, that means your L is, sorry, L is here and R is here, so you're only looking at this cell. So what is the minimum? 7. So this value for this, I mean, it would just be the A1 entry, A0 entry. This will be A0 and this will be
yes,
A2, sorry, A1, A2 and so on.
right, diagonal entries have been found. Now say, what would be the meaning of 0, comma 1? So starting from 0 and go till 1, then basically we would be comparing two elements, isn't it?
Correct, correct, yeah.
So then if I'm filling this entry, I have option of only looking towards the left of this thing. So I'll find the minimum out of the left entry and the entry
The
which is there
currently
at
value,
this
yeah.
A1. Yeah. So in this way I can do something.
Yeah. So yeah, let me just take this same example here. Okay, so okay, so you have 0 1 2 3 4. Okay, so um so let us imagine that we are going in this order. So between between 0 for this entry you are only looking at this subarray, so the minimum is 7. For this entry you are looking for the minimum between 0 to 1, so the minimum would be look at this value and look at this value and take the minimum. So again the minimum is still 7. Now you're looking at this 0 1 2 array, so this is the array you are looking at. Again do the same thing, look at the minimum so far, which is 7, which we have already stored, and now compare it with the new element, so that would be -8, and you keep on doing this. This will take order n time. So
Order in time.
yes, so what are we really doing for writing? Let me call this matrix M of I comma j is nothing but minimum of M of I j minus 1 and A of j. That's it. Right, look at the minimum so far and compare it with the next element. That's it. So this is exactly what we will do everywhere. So each row is going to take you order n amount of time. Okay, and there are n rows, so altogether this is order n square time.
Where?
Right. So, and you can't do better because you have n square sized table. It will take you order one time to write every entry. So order n square is not negotiable, so you will anyway have to spend that much time. So this is in some sense asymptotically the best that you can do. So but this is just a one time effort. Once you have made the table, this time is not something we will care about. This is something we spent so that the subsequent queries become easier. After this point, no matter how many queries come up, you will be able to answer them in order one time. That's the advantage.
Yes.
So what are the two algorithms so far? You have
But then, do we have any relation in between L and R, because this table could be symmetric around the diagonal set?
yeah. So if you define this problem to be L less than R, then these entries are not even required because it does not mean anything, right? So it's like n square by 2 space. But if you say that this is symmetric, nothing is smaller than the other, then you just look at those two indices, look at the subarray between them and answer. So then in that case these would be symmetric entries, like so mirror with respect to the diagonal.
But order will be still order n square only.
Yes. Time and space will still be order n square. Yes.
Yeah.
So this was the first algorithm, and now we have something different. So the second thing is we maintain a lookup table, and okay, by the way, when we talk about time, we are talking about query time. Okay, this is important. We're not talking about the time required to make the data structure. Okay, so this is order one query time. You are just looking at the entry and answering that. That was the advantage, but the space that we required was order n square. Okay. Okay. So now the question is, I mean, these are two extremes. Here you are doing great on space but bad on time. Here you are doing great on time but bad on space. But let's say n was very large, 10 to the 5 or something. Then I don't have 10 to the 5 square, which is like 10 to the, so if n were 10 to the 5, then the space that I need here is 10 to the 5 square, which is 10 to the 10, and I don't have that amount of space. This is huge, right? So I should not have just two options, that either you have this large amount of space, or if not, then you're just doomed in terms of time. So can you do something in between? Maybe I don't want to give you order n square space, I'll give you something like order square root n space, but can you give me a time which is better than order n? That's the question. Okay, so if I were to give you only order square root n order square root n space, can you do something better than order n, maybe log n or square root n or n to the 3 by 4, something better than this thing? So what, I mean, can you think of some um, ideas?
So, like say, uh, can we break this? Like say we have an interval from I to j, and the value of say I comma j is stored there in the table. So we can break it into the interval kind of the thing. Say I to k, and then from k plus 1 to j, and then we find the minimum out of I to k, and then we can reuse that value. I mean to say, because we cannot. So the thing is that if you want to reduce the space, so first thing we can try is the reusability, and the second thing which we can try is somehow if we can find the frequently used values, and so if you want to bring it, reduce it, then interval is one option, and then frequently used values if you can identify could be the other one. But I don't know
Yeah,
how to do
yeah,
it.
yeah. So for now, let us assume you don't know the frequently used values. Let's say that if the probability distribution is uniform, let's say we don't have that information, but the interval thing is nice. So one such algorithm you have seen is um, something called powering algorithm, right? I don't. So I'll come back to this part later, but since you mentioned the intervals thing, let's talk about the powering algorithm. So what does it do? Um, okay. Um, I'll get the same array again. Um, next. Okay. So I will recall powering algorithm. So what does it do? It will, yeah. Um, it will break your data structure, like so. Let's say you are at 0. Okay. Let's say I fix my L to 0, and R can be something, it can be 2, 3, anything up to 7. Okay. So what it says is that I will store in my array the minimum from um, okay, of let's say R is 0, then let's say R is 2. So I'm just looking at powers of 2. So this is L is 0, R is 3, L is 0, R is 7. So these are the powers of 7, as in this is an array of size 1, this is an array of size 2. So array we are looking at is, values we are looking at is minimum of 729. Here you're looking at minimum of 729 minus 8, 9. Here you're looking at the entire array up to 2. Okay, so let us say that I'm only going to store these values. Okay, so what is the minimum here? It is 7. The minimum here is still 7. The minimum till this point is minus 8, and the minimum in the entire array is minus 8. Okay, so you do this for every point. Okay, so suppose I were to change the value of L to 1, then if L is, in general, if L is I, then the value of r's that we are going to deal with is I plus 2 to the 0, I plus 2 to the 1, I plus 2 square, and so on up to I plus 2 to the log n, which in this case is 3. Okay, so that's what we're going to do, keep the minimum like this. So how much space did we use for when L is 0? You are storing 4 values, which is roughly log n. Okay, so this is log n plus 1. Okay, I'll just call it log n. And for every possible value of L, so L is ranging from 0 to n minus 1, each of them takes log n space. So overall you are spending overall space is n times
n times
order log n, which is n log n. So this
n
is
log n.
correct. So this is still better than n square. We are not giving n square space.
Yes.
Now, yeah. Now the question is, if a query comes, how do you find the minimum now? Given that you have this extra information that's being stored, let us say that, again, let me just take L to be 3 and R to be 6. So this is the set of values that come to you. You have to find the minimum now. So how would you use this information?
So I will take the help of this L0 and R3 first. And then I will take the help of this. This is not going to work.
Oh, actually, sorry, this should be minus 1, because finally the size of the array is a power of 2. That's what we are doing.
Yes.
Okay. So if L is 3, what are the R values that we have maintained? 3 plus okay, so this is going to be 3, this is going to be 4, right? 4, this is 6, and this is okay, this is not even valid. Okay, that's all. Okay, so I already have this value stored, right? If R is 6 and L is 3, then I will just look at the entry here. So let me call this matrix B. I'll just look at 3 comma 6, and this is going to give me the minimum. It has stored this value, so which is 4, right? Is this okay?
Yes, ma'am.
So, but this is because we were lucky, because we had this value of R stored. But let's say R were 5 and L was 2. So, or let's say, yeah, L was 2 and R was 5, let's say. Is this fine? No. Let's say R was 4.
What this login stuff here is? I mean, how did we get this off the order of login?
So you are only storing, let's say you are starting at 0. There are n possible values for R, but you don't keep minimum for all of them like we did here, right? You keep minimum for all possible values. You are only going to keep these values. Keep this one, then yeah, 2 steps from here, 4 steps from here, yeah, so 4 steps from here. So you don't keep like all the information, just keep till powers of 2.
Uh-huh.
हाँ.
Uh-huh.
So just keep these values.
Right. How is this going to help? Because if we find the value of r somewhere in
Hmm.
middle or somewhere in there.
Yeah, exactly. So now what you could do is, um, let us say I want to find um, a minimum from, okay, let's say 1 to 6. This is not a power of 2, no? 1, 2, 3, 4, 5, 6. Yeah, this is not a power of 2. So I have to find the minimum here, but I only know this part. I know this part, and then I know the whole part, but I don't know the minimum till here. So what you do is you take the maximum jump that you can. So what is the maximum jump you can take using power of 2? Still 4, right?
Yes.
Huh. So now what you do is keep a minimum from um, array 1 to a of 4. Okay, this will tell you a minimum here. Okay, now what you could do is, if you start from here and keep on looking for powers of 2 until you exhaust, that will still take you a lot of time before you exhaust. So what you do is you start from here and go as much back as you can. Okay, so from 6 you go, what is the maximum you can do? You can do this,
Okay.
or you can do this, or you can do the whole thing, but like this is the max you can do. So you also find minimum from a3 to a6. Now some overlap is bound to happen. First array was this, the second array is this. There is some overlap that happens, but we don't care about it. We're only looking for a minimum. So the minimum has to be this, either this or this, right? So these are the two values that are stored in your table. Just look at the two values and find the minimum from there. So that is your algorithm. So if you are given an arbitrary L comma R, what you will do is from and let's say L minus R is okay, let us say that L minus R is between 2 to the k and 2 to the k plus 1. Okay, so now what you do is you look at this value L to L plus 2 to the k minus 1, and look at this value, which is um, R comma R minus 2 to the k plus 1, right? Mm. Yeah, okay, so look at these two values, these are already there. Okay, and now you find so this is order 1 time, this is order 1 time, because these are stored in the table. And now you are going to find the minimum of BL to L to the 2, okay, and B of R minus 2 to the K plus 1 and R. That's it. And that is your answer. So you are still running in order 1 time in terms of queries, but you have reduced the space from n square to n log n. So that was the algorithm you saw in class. So this was order n log n space, but order 1 time. So is this okay? Uh, okay. So so there is one comment here which says that is this the fast method for calculating number raised to? Yeah, I mean, the name is similar and the intuition is similar, that using powers of 2 you are making logarithmic amount of savings, but essentially these are two different I mean two different algorithms, but the intuition or the core idea is similar. You are skipping a lot of things by jumping with the power of 2. Right. Okay. So this was the algorithm that was done in class. So some of you might have already seen it, but okay. Um, huh. So now
What about root n, ma'am? Third
yes,
one?
yes. So can you do this blocking in some other way instead of doing this powers of 2? Can you divide it into some other way, some other blocks? Use that information um, to get the space even better. Okay. So let us say that, so we want further improvement on space. So now assume that I'm going to break my let us just say I'm going to break this into k blocks of size k, and for the sake of simplicity assume that it's completely divisible, all the blocks are of size k, otherwise you can handle that easily, but let us assume that this is what we're doing. So this is b1 b2 up to bn by k, because the total size of the array was n. Okay. So what we are doing
Whether the
is
k is L minus R, ma'am?
L minus R. No. So you don't know anything about L and R for now. Okay.
Okay.
So divide the array A into blocks of size k. Okay, and let us say that the b1 to b1 b2 up to bn by k, these are the blocks that we have. Okay. Now suppose you can okay, now suppose you can you are going to introduce a data structure now. Okay, you're going to use some extra space. The extra space does the following. So I'll call this array A. It is of size n by k, so 0 1 up to n by k minus 1, and what it stores is m of I stores the minimum element in block bi. Okay, so with respect to the with respect to this algorithm, what we would be doing is I will divide this into this is my first block, yeah, this is my third block, this is second block, and this is fourth block. So these are the 4 blocks. What you do is keep minimum of this block. So what is the minimum is 7. Keep the minimum of second block, that is minus 8. Keep the minimum of third block, that is 11, and keep the minimum of fourth block, that is 2. Okay, so for me n was 8 and k was 2. Let us assume that for now. So you get this array now, which I call m. Now what you do is, let us say L was 1 and R was 5. Okay, so this is the sub array that we are looking at. Then the minimum has to be either this or the minimum of this block or the minimum of this block. So so within this block you know the minimum, that is minus 8. You don't need to find it, you'll just look at this array and this is what you have. For this block you know the minimum, that is 11, but we can't use the minimum here because the minimum of this block could be 7, but 7 is not a part of our array, so that is where you go wrong. So if a block is entirely contained within L to R, so for all okay, so let us pictorially see this. So if L is here, R is here, then you visualize this in terms of blocks. Okay, there may be many blocks in between, and R may be in some other block. So I'll call this bi plus 1 up to bj, let's say. So the minimum has to be between L to this value. Look at the minimum here, look at the minimum here, and let's say R is somewhere here, then the minimum here. So only these two are behaving differently. All these values I already know because they are stored in my array M. So all these values I can pull off in order one amount of time each, right? And to find, okay, so there are two things. One is for the blocks completely contained in between L and R, what you will do is use M to find minimum within each block. So how many blocks can be there between L and R, like a rough bound?
So in between 2 2 raised to the power log something.
How
In between,
many blocks are there? There are n by k blocks. So
okay.
so worst case, let's say there are order n by k blocks, because if L is in this extreme and R is in this extreme, then you have so many blocks, right?
So, but then I have a doubt here. Why don't we maintain the directions here? Like while formulating this n, we could have maintained a direction that okay, we got this value as -8, but this is the left element of this block, because now we are considering the blocks of the size 2 only, and whether this is the right value or the left value sort of the thing.
But
So then, since we are left with only 2 singletons, that too only on the extremes. So then we could say that okay, since we got this, so then probably with the help of this left and right directions, and by using some extra space, we would be able to solve these singletons easily.
But what if, so that is because in this case I chose k to be 2, but k can be something like log n or square root n.
Oh,
So
I see.
there are okay, but I mean, okay, let us come back to the analysis. So there can be like in the worst case there can be order n by k blocks, correct? So these were b1 to bn by k. So assume that we have order n by k blocks. For each block, you are just referring to this entry in M. Okay, so find the minimum element of each block. This will only take order one time each, because we have stored these values, because these are stored in M, right? So in the first step, for finding minimum of each of this, we have spent order n by k time. Now you have to find the minimum. So like you said, k, if k is 2, you can store some whether it was left element or right. But if k is an arbitrary number, what you could do is just use your linear search. your linear algorithm, which is this one. It takes order and time, but what is n for you? You're looking inside this array, which is of size k, correct? So this is an array of size k, and you are running your linear uh, time algorithm, which is just scan from L till the end of this block and find the minimum. Size of this uh, block is only k, so you are spending order k time here. So step 2 is find minimum of from L to the end of block. This will take you order k time because size of block itself is k. So we are using linear search thing. Okay, and same thing you do at the end as well. You want to, maybe R was not fitting exactly here, R is overflowing in the next blocks, so you look at this part of the sub array and find the minimum again. So do the same for, repeat for R. Okay, so this will again take you order k time. So what is the total amount of time we spent? It was order n by k plus 2k. So this is roughly order. Okay, so this is the total time. Okay, and just to visualize what we did, you looked at this subarray, looked at the blocks. Here one is not completely contained within the block, so you linearly find the minimum. The minimum here is 29. Then just fetch this value. For this array, you look at this value, you get -8. For this part, this block, you look at the value again, you get 11, and compare these. Find the minimum of this turns out to be -8. That's it. So the saving is happening here in the intermediate blocks. So is the algorithm clear and the time analysis is clear? Okay, so now the point is, what value of k should I choose so that this is minimized?
K to be equal to n.
But L is something that is not fixed. L and R will keep coming, they will keep changing, but this data structure that we are making is a one-time thing.
Yeah, so let us minimize this function. Let us say k is equal to x, so we get n by x plus x. Differentiate this thing, and then probably we'll get this value x is equal to the square root of n kind of.
Yeah.
So for the square root of n, this entire thing will came out to be order of square root of n.
So if k is very small, then this value is small, but this will be larger. This would dominate. But if you choose k to be large so that this quantity is minimized, then this quantity becomes large. So the sweet spot would be when they are both equal. So the minimum the minima is achieved when n by k is equal to k. So this implies k square is equal to n. This implies k is equal to square root n. So if you choose k to be order square root n, then the time taken by the query time is n by square root n plus 2 times order square root n, which is still order square root n. Okay.
Not only this, even if we differentiate this, even if we use the normal technique of the minima, then also we'll
sure.
get the result.
Yeah, that's correct. Yeah. So now what you have got is order square root n space and order square root n time. So the idea is by maintaining blocks.
Blocks.
It's not a standard name, I think I'm just calling it blocks. Okay. um, okay. hmm. Now can you think of something, can you modify this idea, okay, this idea of maintaining blocks? Okay. So I'm okay, the target that we would want is okay, like the target for today would be hmm, okay, I want to bring the time down to order login from order square root n. At the cost of that, I would end up spending something more. um, let's say I'll do n log n. Okay, so this is still incomparable. Okay, wait, sorry, it's not n log n, it should be n by log n. Okay, so if I compare this algorithm and this algorithm, I'm spending more time but I'm saving some space. And if I compare this algorithm with this algorithm, um, I'm doing better in terms of time but I'm compromising in space. So like this is intermediate between these two. Okay, so can you combine these two ideas, because this one seems to be taking more time, this one seems to be taking more space. So can you use sort of best ideas of both of them, and like just essentially combine these two ideas to achieve this? So
Divide into the blocks and keep on halving the blocks every time.
mm,
So
hmm,
maintaining block is one thing,
hmm,
and so basically we have to cover a range from say 1 to n in such a way so that yes, this is there given in the problem itself. So we divide. Initially, we use bigger blocks, and then we use smaller blocks. And the blocks should be such that we should be able to clearly distinguish in between the left half and the right half.
hmm,
So,
hmm.
uh,
Okay, let us do one more thing. So let me choose in this algorithm, okay, in this algorithm itself, let me choose k to be log n. Okay, so we had order n by k plus order k time algorithm, but let me choose k to be log n. So what will happen is I have blocks b1, this is of log n size, sorry, b2, and so on up to b n by log n, this is also of log n size. Okay, so what does this come out to be? This will be n by log n plus order log n. So but still the dominating term is n by log n. Okay, so okay, so where is this I mean where is this log n thing coming from? It's coming because if L were here and R were here, then I'm going to do a linear search here and a linear search here. So this linear search for L and R, these would incur as cost of order log n. This is fine, this is something we will pay. But then what we're doing is for each block here we are storing minimum. So this is the minimum for block 2, then we have minimum for block 3 up to, so these were the boxes in between whose minimum we were storing and finding a minimum here. So what is the size of this n? M stores minimum element in each block. So what is the size of M? Um, is this I hope this is making sense, right? So we have n by log n blocks, so for each block there is one entry, so there are n by log n many entries, right? This is minimum of b1, this is minimum of b2, bn by log n and so on, correct? Now what happens is, when you look at your L and you look at your R, you are looking at a series of blocks that lie here. So let us say that these are the blocks in between. Is that making sense? So
Actually, this is not that clear.
okay, so let me just take an example. Okay, so assume that I had an okay, let's say I have an array of size 16. This is the initial array that was given to me. Okay, so n is 16 for us, and I'm saying k is log n, right? I'm choosing k to be log n. So what is log of 16? It's 4. So that means we are going to divide this into blocks of size 4. So okay, so okay, for the sake of simplicity, I'll rename this to 1 to up to 16. Okay, so how many blocks will be there? This is one block from 1 2 3 4, 5 6 7 8, this is another block, 9 to 12, this is third block, and 13 to 16, this is another block. So this is b1, b2, b3, b4, right? And now what we did was we stored this value. M stores the minimum among these values. Okay, this is the, okay, let me just write random values now. Minus, okay, 13, 17, 2, and let's say 19. So the minimum here was 2, it stores this. Let's say this was 4, 9, 19, 1. So this stores the minimum of block 2, which is 1, and you do the same for this, and you do the same for this. Fine. So what is the size of M? N by k, which is 4.
Yes.
Yeah. So now let us say that L is 2, and let us say that R is 14. Okay, then what does the algorithm say? I want to find a minimum from here to here. Let me find a minimum within this block. Let me find the minimum here, like within this block before R, and find minimum of b2 and b3.
Yes.
Okay, but the minimum of b2 is already stored here. That was 1. So I don't need to go and find it. I will just look up this value. So I will look up this value, and similarly the minimum of b3 is something that is stored here.
Yes.
Right, and this is something we will find linearly. It is only a size k block. Just scan from L till the end of block, scan from R till the end of block. This is just order k. So this is something I'm willing to pay, this order log n, because I chose k to be log n. So this is something I will pay. But what is really happening is, let us say that this was a large array, and there are so many blocks in between. So if n is, for example, 2 to the 8, and k is 8, k is um, log of 2 to the 8, right? So there are going to be so many blocks in between, right? These will be too many. So what you are essentially doing is, when instead of finding minimum of this, you're basically finding a minimum in this block.
Right.
Right. So if these were the blocks whose minimum I were to find, I'm just actually going to look at M. Yeah, look at their corresponding values. There are only 4 values here, and this boils down to finding minimum of blocks bi to bj is same as finding minimum of m, minimum in the array m, with l is equal to I and r is equal to j.
Yeah, so same algorithm can be used recursively.
Exactly. So exactly.
So yeah, so that will, yes, so that will break this. I mean this thing, which in fact got n by log n into further by some amount, and what that amount would be n by log n square, I guess. Which can. So I mean, if we are having those many numbers n by log n number of the points, and if we are looking for their minimum elements, and if we are using the same algorithm recursively, so that n by log n number of the things will get further broken down into how many things? Say
Yeah. So
n by log n square kind of thing.
no. So this is your array of size n by log n.
Yes.
So and what was the um, so what is this, the time you would need for this? That will be log n by, sorry, n, capital N by log n,
Yes.
and just
So that.
replace n with, yeah, so this will be n by log n by log n, and these terms will just keep adding, but
Oh yes. Yes.
this will keep happening. But the point is that we are not we can, so these are just additive term, right? So we are not saving, this will only be larger than n by log n. It is at least, the sum is at least n by log n, right? But I want it to do better. I don't want this n by log n factor. So what if you use a powering algorithm now, instead of doing using, so you're right, this is essentially range minimum query with respect to this value, but let us not use the blocking again. Let us use powering now for m.
Yes. So powering will need to multiply this by n log n amount kind of a thing. N log n amount. I mean, because powering was doing this thing in the effort of in the space of n log n, and in an effort of
Yeah,
in the space of
powering was,
n log n.
no, powering was yeah,
Log,
n
log
log
n.
n log n
N log
n log n with order one time. So let me come back. So okay, so now if I use powering here, okay, so what is capital N? Capital N is n by log n, and use powering on this capital N sized array. So what is the space that it will use? Space will be capital N log n, which is n by log n. And we are just replacing capital N with um, log of n by log n. Okay, and what is the time that it will take? Time it will take is just order one, right? So we don't need to worry about time here. But is this analysis clear? Like, the main observation is that um, This is the main observation, that the following problem is an RMQ query. Right. So then we are saying that use a powering algorithm here. So okay, so just to summarize what we did, we divided this into blocks of size k. Your L is here, R is here. Treat the first and the last block separately. Just look at the middle blocks. We want to find the minimum of all these blocks. We say that this is same as finding a minimum in this subarray, which stores the minimum here. So this is just going to give a mapping from blocks to their minimum. Now we want to find a minimum here. Okay, to do that, so this, using the blocking here, saved us time in finding this, but in order to save time in finding this, we are going to use the powering algorithm. So instead of n by log n, we will, instead of this whole thing, we will end up only using okay, what does this turn out to be? This should be order n. Yeah, this is actually order n, slightly smaller than n, because this log n and this log n will anyway cancel out, and then you are left with log n by log 1 by log n, which is a very small quantity. So this is actually smaller than order n. So what is the total space that we used? Okay, so space is n by so total spaces, first we are maintaining an array m. This will take order n by k, which is n by log n space, and yeah, and then we are using the powering plus powering, so that should take us okay, am I missing something in the analysis, or okay, let me just go back. Okay, that's sure. Okay. And that is going to cost us order and space extra, but overall so overall this is order and space, right? This is the larger quantity. So okay, and in terms of time, we ended up spending order k for L and R separately, plus order 1 for finding the minimum of the block. So this is still order log n, because k was chosen to be log n. So okay, so this is actually order log n, but space is order n. Okay, so space is order n. So, but is the overall algorithm clear, or are there any questions about the algorithms? Okay. 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 So okay, but this is not the best you can do. Actually, you can get this even even better. But um, yeah, but we will not get into that algorithm. If you're interested, you can look it up. Um, there are even better, even cleverer algorithms for this data structure. Um, okay. So another follow-up question which I will just write, but we will not do it. So um, just try this out later. This should be simple. So next question is, instead of array, if I were given a matrix, if I'm given a matrix of dimension m by n, these are all integers, and the input that is going to come to you are four values: r1, r2, c1, c2. So that means you will look at row r1, you will look at row r2, look at column c1, and look at column c2. Look at the submatrix contained here. So look at this intersection. Okay, so let us say that this is the intersection. This is the submatrix defined by rows r1, r2, and column c1, c2. And the question is, find the minimum in this entire submatrix. Output the minimum of m um, with r1, r2, c1, c2. Okay, so this is a natural extension. Instead of array, you are given matrix, and so you want to um, yeah, we want query time. What is the best query time you can come up with, and what is the space that you will end up taking? So look at the trade-off between the two of them. So you should, if you apply different strategies, you should be able to see similar trade-offs. But like this should be very similar to the array. So we will not we will not get into this. Okay, and note here is okay. Okay. Uh, Another question that is related to the range minimum query is what is called least common ancestor, or LCA. Okay, so what does that mean? The input to you is a tree. So okay, I'll write the problem formally later, but um, assume that for now, assume this is a binary tree. Okay, and let me look at so this node here and this node here. Okay, so how do we define the least common ancestor for these? You look at the first parent of these two nodes, which is a common parent of these two nodes. So okay, so for this node, every I mean, this is the parent of this node, but this is the parent of this node. So everything from the root to this path is an ancestor for this node. Similarly, for this node, everything along these lines is its ancestor. Okay, so so ancestor is of a node I is basically um, parent of I, parent of I, and this goes all the way. You can do parent of parent and so on, right? All the way up till you reach the root. So the root is an ancestor for all the nodes. So if I give you any two nodes, the common ancestor is always root. But I want to find the least. So let us say this is at a higher level, this is at a lower level, and so on. So by least common we mean we want a common ancestor as low as possible. Okay, so if I were to change this to this node, then of course this is an ancestor for both these nodes. This is also an ancestor for both these nodes. This is also an ancestor for both these nodes, but this is not. This is only a parent of this, but not of this. So the least common ancestor for us is this. Find a common ancestor as below as possible. That's your answer, and output that. So in this case, the output should be this one. Okay, so you are given a tree. Assume it is a binary tree, need not be complete. Input that's coming to you is two nodes, n1 n2 in the tree, and you want to output the least common ancestor. Okay, so in this case, the least common ancestor of least common ancestor of 1 and 2 is 3, even though 4 and 5 were the ancestors. Okay. Okay. So I hope the question is clear.
Yes, if you assign the node numbers starting from the root as 1, so in that case, the left child will be having the index 2, the right one will be having 3, and then so on. So in this way, if we assign the numbers, probably the first yellow one would be having the index 1, 2, 3, 4, 5, 6, 7, 8. Its index would be 8. And the index of the second would be, say, 9, 10. Because the parent of 8 would be having the index 4. And the first yellow node, whose index
Okay.
is 8.
Let me just draw that.
Yeah.
Uh, Okay.
So now if we assign the proper node, if you do the proper numbering of these nodes,
One.
with the root starting as 1, yeah, 1, 2, 3. If you can assign, yeah, 4 to the other nodes as well, 6, 7, and then 8, 9, 10, 11, 12, and 13. So now since we are looking for the least ancestor, least common ancestor, right? So the ancestor of 8 would be having the index what? 8 divided by 2, 5, and 13 would be having the ancestor like No, this numbering has, because a node having the index I would be having its children at the node 2i and 2i plus 1, isn't it?
That is true for a complete binary tree. When all the parents have two children, then what you're saying is true. Um, but this is an arbitrary tree, so some of them may not have children and so on.
Oh, so in this case, then I have no other option except traversing upward and then find the least. Right.
So what is let us analyze that algorithm. So
Which algorithm?
the one you were saying, what you do is look at the ancestors of 8, look at the ancestors of 13 and find the
So I
least.
so yeah so if somehow if we can convert this, because this is not the complete binary tree kind of a thing. So if we can bring it into the because the conversion of any tree to the complete binary tree is not possible. I mean, we can convert a general tree into the binary tree, but not a binary tree to the complete binary tree. So then the I mean, getting the common ancestor would be difficult. But I'll have to traverse, like say for 8 I'll have to traverse up in the hierarchy, and then for 13, and then we find the one which is the lowest.
Yeah. So first algorithm is find um, ancestors of n1. So this is going to be a list of size order n. Let's say worst to worst case. So this list 1 consists of ancestors of n1. Let us say this is of size order n. That's like the worst to worst case. Total number of nodes in the tree is n. So for us n is 13 here. Okay, and similarly find ancestors of n2. This is another list. This is of order n size, and yeah, and now find the so so actually this is like finding maximum number which is common to list 1 and list 2. That is the least common ancestor. So does everyone, so observation is that maximum valued number value common to list 1 and list 2 is the least common ancestor, because let us run this example with n1 as 8 and let's say n2 is 13 again. So what is list 1? List 1 consists of all ancestors of 8, which is 5 to 1. So you have 5 to 1, and list 2 consists of all the ancestors of 13, which is 9, 5 to 1. So you have 9, 5 to 1, and what did we say? Find the maximum value which is common in both the lists. So what is common to both the lists? 5 to 1, 5 to 1. And what is the maximum among them? Maximum common value is, or maximum value in L1 intersection L2 is 5. Okay, why is that happening? Because we numbered it like this. The way we numbered is the nodes at the top level have a smaller value, the nodes at the bottom level have larger and larger values. That is what is happening. So yeah, so the least common ancestor according to this numbering will always have larger value. Is this fine with everyone? Yeah, you will do something like BFS or DFS to find list 1, list 2. This is your order and time algorithm. Okay, order in time and order in space. So this algorithm takes CQ with BFS or DFS. This will take time as order n and space as order n. Okay, so so again, like you know the question, we want to do better. Um, okay, probably you can save on space as well, but okay, let me not go there. So the point is, you can actually do something similar to what you did earlier. The difference is that now you have a tree, but there um, you had an array. So um, I mean, do you see any similarities with respect to the previous question? Any thoughts?
We are looking for common summary. I mean,
Hmm.
from the tool list, we are looking for the common summary, and once we have the common summary, we are looking for the minimum amount of
Hmm.
minimum element in that
Hmm.
common summary.
But how do
So
you visualize? How do you visualize this tree as a subarray? So if you could somehow convert this into, so this is kind of a reduction. You are given a, a tree and you want to find the least common ancestor. You want to convert it to the RMQ question. So how will you translate the tree into the array? Yeah.
So that's fine. That's fine. We can. I mean, in this way only, we can convert this tree into a list. The root starts from the index one, and then we are having the left. I mean, need not. I mean, but then the condition here is that this is a binary tree. May not be the complete binary tree, right?
Yeah.
So then we can, yeah, use these indices to form a list, and then we have this problem. The problem we solved earlier. Range problem, isn't it?
Hmm.
Where is the issue in converting this tree into a list in this way?
Hmm. Hmm. So let us do one thing. Let us write. Okay. Yeah. I'll copy this. Okay. So our idea is that, or our goal is that we want to convert LCA problem into RMQ problem. And why do we want to do that? Um, because here I had I had a trivial answer similar to what we did earlier. We had n square size table, then we were trying to do all the trade-offs. You can do a similar thing here, but if you could just reduce this problem into this problem, then I can use all the answers for RMQ and get all the answers back here. So if I had um, I mean, whatever algorithm was working for RMQ, I will just copy paste and use it for LCQ. So these are called reductions. If you have seen, you can relate to this. If not, that's also fine. You don't need it for the discussion. So that is the idea. We want to convert this to RMQ problem, but the input here is array. The model you are working here with this array, whereas here you have a tree. So we want to convert tree to array in a meaningful way, so that answers here can give you answers there. So let us do one thing. It may sound very magical right now, but once you understand the algorithm, you'll know why we are doing a DFS. So let us do a DFS and store that into the array. So let me form an array A in the following way. You start the DFS at 1. So what do you see next?
Oh, so then 1 to 2, will we
1
go
to
to
2.
2? 2 5 9
4
and
4
then 13 say.
you will do this, no? 4.
Okay,
Huh.
we
4.
can go for the. Why don't we go for the lengthiest one? Go for that.
Why don't we go for the
Let us select the lengthiest path and then we go for 1 to 2 and then 2 to 5, 5, 9,
mm,
13.
what it does is it will always okay, sorry, let me do a okay, so what I meant is, sorry, a pre-order traversal.
Oh, okay,
Sorry,
okay, all
yeah.
right.
uh, so we are doing left, go to the left child, go to the right child, and then sorry, so I should not have written this, no? So am I okay, wait, sorry,
Pre-order
sorry,
would
let me
mean
wait,
that
sorry,
root will get first, root,
sorry.
left, and then right.
uh,
Post.
post is you visit and you go to left and right, right? mm, so basically what I want to do is this: visit, go to the left, go to the right. mm,
Hello.
yes.
Post order left root right. Left right root.
Okay, so this should be, so this corresponds to pre-order, right? Thanks. Okay. So I meant a pre-order. Okay, thanks. Okay, so okay, so let us do this VLR, pre-order traversal. Hmm. Sorry, yeah. Can you tell me the values?
1, 2, 4.
1 to 4. But
Then back to 5.
hmm. But okay. So okay, a slight modification is you keep on going like this, but every time you go back, you write it. Okay. So okay, I'm very sorry for the confusion. This is not the correct name. Okay, what I mean to say is, um, okay, you visit the route, go to the left, so write that, go to the left, write that. Now you can't go further and you're coming back, so you write that as well. Okay, so this
Okay.
is slightly different. Sorry, should not have. So, mm, okay, the screen share. Huh. Okay. So sorry to confuse. Okay, what you do is, now you go. Okay, just keep exploring, but every time you reach a node, you're going to write it. That's all. So can you tell the rest of the values? So this is the path we followed so far. Now you're going to explore the right child. Huh. Yeah, you do 5, 8, 5, and now you're back again. Um, yeah, next. Yeah, then you do 9, you go 12, you come back to 9, go to 13, 9, then you will go back to 5, 2, 1, and so on. Okay, from here you will start the other tray, but this is very long, so let me not write these values for now, but you will have values corresponding to this as well. Okay, so what is the size of this array? Give a like a rough bound. If the number of nodes in this tree were n, then what is the size of this array?
Order n.
Order n. It is at most, the blow up is at most doubled, because every sorry, yeah, because um, every entry here occurs at most twice. There are some repetitions, but they um, okay. Okay, not exactly twice, but sure. Okay. Okay, this is something I will come back to. So we need to analyze the space of this. There is some blow up. Analyze space here. Okay, this should be order in, but okay, I'll come back to this. Okay, so we want this to be order in, but let us assume that you have this array now. Can you see a range minimum query here? So let us say that the least common ancestor we wanted to find was 9 and 13, 8 and 13, but okay, in this case we are really lucky we don't have okay, we'll do step by step. So let us say that I want something which has repetitions. Okay, let's say 5 and what is a good okay, so the issue with 8 and 13 is that it's not a very good example because it occurs only once. So if I have to find the least common ancestor of 8 and between 8 and 13, I will locate these values in the array and find the range minimum query. So take this as L, take this as R, and find the minimum value in this subarray. What is that? That is 5, and that is indeed the least common ancestor. But the issue will happen when there are repeated entries, right? So for example, 9 here occurs several number of times, 5 occurs several number of times. So then which one will you take as your L and which one will you take as your R? So the algorithm is that convert uh, tree to array A, then take node n1 as your, so we want to relate n1 and n2 to somehow to L and R. And once you can do that, then you just want to use the range minimum query algorithm. So whatever nice algorithms we had there, you can translate it back here. So if there are repeated occurrences, which one is the correct uh, to take? Yeah, exactly. So what you will do is you take the in this array the first occurrence of n1, that is going to be your L, and the last occurrence of n2 is going to be your R, because this is intuitive, because the first time you visited a node, you're actually going to
Yes.
yeah, trace back the subtree that it is rooted under. You're not really looking at these values, you're actually looking here. And uh, the last time you visited, for example, 9, okay, the last time you visited 9 was when you came like this is the last time, right? After this point you're only going up, right? So you're not exploring whatever, like everything that was below it is already contained in your array. So that is why we make this choice. And if you think, spend some more time about it, it will seem very natural why we considered this ordering and why this choice of LNR was made. So I will just leave it at this idea. Okay, but do spend some time here, and you should also be able to find this literature online. So make sure to um, that you agree with this idea. And we have, yeah, okay, fine. I'll not be able to cover the questions on linked list right now, but if there are any questions about um, okay, this algorithm in particular, then do let me know. Okay, and there was some comment here. Okay, where did it go? So there is some error in assignment 5, right? So use the discussion forum. There are other TAs who handle those things. So just put your doubt there, and they should uh, clarify it maybe in a matter of few days. Okay. So okay. So next we will meet tomorrow. The next tutorial is at same time 7 p.m. to 9 p.m. So hopefully we will get to discuss more on linked list tomorrow. Okay. So I'll just write that as well.
Thank you very much, ma'am.
Thank you. Mm. Okay. So thank you all. I will upload this recording as well. Okay. So
Thank you so much. Thanks.
thank you.
Bye.
Bye.